Amabel.
My name is Hans.
And we are presenting a senior design project, which is about the design of a 3D prosthetic socket.
Our faculty advisors for this project are Dr. Roche, Guzman, and Dr. Mohamed, Abdelmegeed. And so let's get started.
So the bioengineering problem that we're tackling today is amputation, specifically the lower leg. So 20 million Americans are currently living with limb loss, and roughly 35 to 40 million people worldwide. This limb loss affects loss of mobility, causes loss of mobility, muscle weakening, and joint stiffness, reduced ability to perform daily tasks, causes dependence on other people, caregivers, and also causes emotional challenges, including depression and loss of confidence, anxiety, etc. But the main problem that we want to address, that we're concerned about, is swelling. So the causes of swelling in an amputation are post-surgical inflammation, which is just the body's natural reaction to the loss of tissue damage, and venous insufficiency. So that is when blood pools at the bottom of the residual limb as a result of a lack of circulation. Also in the lower limb, there are blood vessels that have valves that aid in the circulation of blood from your lower extremities back up to the heart, because it facilitates blood going up while preventing the gravity to pull the blood back down. And lymphatic disruption is somewhat similar to venous insufficiency, and that's just related to extra fluid buildup. Another cause is inactivity. Since the limb is now amputated, there is a lack of muscle contraction, and another way that the body naturally brings blood and fluid back up is via muscle contraction. And the lack of muscle contraction also causes that. And comorbidities that worsen swelling are diabetes, and diabetes affects swelling in 60 to 70% of amputees, cardiovascular disease, kidney disease, and medications that cause swelling as well. However, it doesn't matter if a patient deals with one of these comorbidities, they are still prone to swelling, simply as a result of the lack of circulation and blood flow. So the two types of swelling are immediate swelling that happens after, and that causes the volume to increase by 10 to 25%. And in the long-term phase, which is after 10 days post-op, the limb volume fluctuates by roughly 5 to 10% on a daily basis. And that's problematic when it comes to having a socket that is set. So first off, what is a prosthetic socket? A socket is the part of the prosthetic device that connects the residual limb to the actual device. And traditional sockets are rigid and they're non-adjustable, and they cannot accommodate to the limb changes that happen as a result of swelling. And poor fit can lead to skin irritation, can cause pressure sores, and can resulting in limited wearing time, and that ultimately means a lack of independence, that causes a lack of independence for the patient, and also a lack of inactivity and simply a decrease in life quality. So another issue is that the fabrication time for a prosthetic socket is relatively slow, and it's usually longer than a week. And a pretty big issue is that they're expensive, they're very costly, and hence limiting accessibility to patients of lower income.
So before we could even find a way to make the socket more affordable and more, so we could match our goal for this for the design. So we need to first dig into the conventional way of making a prosthetic socket. So from our research, we found a prosthetic facility in Long Island here in New York. And when we spoke to the engineer, he told us there's three major parts in making the sockets. So the first part is getting the negative mold. So basically, the residual lamp is put into a cast, and then you have the shape of the residual lamp. And then the same cast is filled with plaster, which is then sanded and sculpted to have the organic shape of the legs. Then the whole thing is wrapped with the material of choice and then baked in the oven for a few hours to, I think, 350 degrees Fahrenheit. So these are the specifications for our medical device. So when addressing the problem, we found that we need to, for this to be successful, we need to address these specifications. The first one is functionality. For the socket to work, it needs to first function. And we have four main criteria for this section, which is the socket must fit. It must be comfortable, meaning that the strain must be 50% or higher. So higher strain, which is the change and which is the deformation of the material, the material needs to be able to deform and going back to its original shape. And it needs to be able to do that to 50% of its shape. So 50% or higher means that the material is comfortable. It needs to be able to support the patient's weight, which is about 500 pounds, at least 500 pounds, because most patients weight less than 500 pounds. And it needs to be suitable for patients that are active. Manufacturing needs to be less than 500 because one of the main causes to make this affordable, and fabrication needs to be pretty short. And these are the standards that we are going to follow for our design process. So this is the facility that we visited in Hicksville. So they're pretty known internationally. They have two facilities in New York, one in Hicksville, and I believe one in Buffalo. So they make everything from treating the patient to getting the mold to manufacturing to also physical therapy. So these are our individual design concept for the sockets. So, and that's our decision matrix, which tells us why we made the choice. Like, because we each designed the socket individually at first, and then we had to choose the best specifications and the best feature of the socket so we could have the best final design concept. So now let's introduce our team design.
So in order to meet our standards that we've made, 3D printing is a very useful tool because it can be used to facilitate cost effectiveness, manufacturing time, and customizability, and even the manufacturing process. It makes it easier.
For 3D printing, we only have access to two types of 3D printers. So basically FDM and SLA printers. For the FDM printers, we have access to materials such as PLA, and ABS that are pretty strong but not really suitable for our design. And we also have resin, which is light based, and we'll see later on that how we're able to determine which material is the best based on what's available in the makerspace. So concept number one, was the first concept that I came up with to fit the specifications. So basically for this one, the material chosen wasn't really the best. It's really strong, but it's also very heavy when the patient will be using it. Plus, it's not comfortable, and it's also too symmetrical, which means that it doesn't have the organic shapes that the legs would have in real life.
So concept two features gaps in the front and back to enable support and flexibility. It was based off of a priorly made socket and was analyzed. The prior socket was analyzed using a software called ENGG, which allows you to find different lengths based off a known length in an image. So ENGG was used to get the dimensions for this concept. And it also has cutouts on the sides. And those cutouts on the sides are meant for panels. And those panels are exactly what helps with adjustability. So the panels are meant to go in and out with a dial. So the hole that is there is for a dial to be placed there, and wires that are attached to the dial. As the dial turns, the wires expand and get smaller, so that will aid in adjustability. And since another issue with this concept is that it is not fully anatomically accurate, and since it's not fully anatomically accurate, it has high failure risk, because that is very important, as I've previously stated in the beginning slides. So a way to mitigate that issue is by using 3D scanning. So we used another priorly made socket that does have anatomical accuracy, and we scanned it using a 3D scanner, and that STL file would be edited in a CAD editing software, and that would help make end up with a good shape. We'd end up with a good shape with that.
So once we 3D scanned the socket that was donated by the prosthetic clinic in Higgsville, so we had to, using the data that we extracted from the 3D scanner, we had to personalize it to our needs. So we used the software called Mesh Mixer, which allows us to work with organic shapes. So we could make the socket hollow, because when we extracted the data, the whole thing was a solid. And we also had to make irregular shapes so we could fit a patient. So here's a short. So basically, they're just having this. They just did the same thing. They 3D scanned the socket, and using the software, you're just personalizing it to the patient. And it's pretty straightforward, pretty easy to use, and that would be the final result.
Alt tab.
order to understand why the first few shapes were not anatomically correct, because you look at a leg, if you're not well informed, you think, oh, what's wrong with the past shapes that we had? But in order to fully understand and correctly understand why and how to get an anatomically correct socket, we have to understand the anatomy of a leg. And here I have images of the leg. And so first thing that, from what I understand, you'd have to go by the anatomy of a bone itself. It's mainly based off the anatomy of the bone. And there are pressure points that need to be observed, and there are certain points in the limb that need space. So the more tough regions of the legs, such as bones, need to be require a concave shape, whereas softer tissue are usually where support is placed, so muscles and ligaments, things of that nature. So in this image here, as you can see, the socket, this would be the beginning of the socket, and that's placed right below the kneecap, where there are ligaments and soft tissue that would act as a cushion and support. So that would be placed there as an anchor to support, and all the support areas are simply where places that aren't bone, basically. So you basically just want to shape the socket based off of the shape of the bone. And these are just the blue. Here signifies, in this first image, signifies this is where support is being placed. So this is usually, this is where the convex shape of the socket is. And the yellow are the parts that need to be supported. Apart from that, there's also, the blue areas are also where the panels are placed, since the other parts need to be supported. So the panels can only be placed, and the moving parts of the socket can only be placed in the blue areas. And the other image is how the socket is shaped around the leg. And this is a real life image and depiction of a socket that is made based off of the anatomy of the leg. And as you can see, this part here is convex, concave. So the same thing was emulated in the next section. So apart from that, our team design concept was to have a fully functioning adjustable socket. So this socket, which was designed in Inventor, emulates slightly the shape that is here. However, it has internal wire tracks for the wire, and the panels are in the same places that they are in the other socket. And now when it comes to the dial, so this is the element of the socket that actually allows it to adjust, to be adjustable. The concept was based off of a instrument, like the part of the instrument that allows for tuning and tightening and loosening of the strings. So this design, the wires would go inside of the holes, and there is a cap that attaches to there's a cap that attaches to that element, and as the cap is placed on top of the key, and the key is placed into that hole in the socket. So that's a hole in the socket, and the key is placed in there. So these are also designed on Inventor 3D CAD modeling. So this was our design. This is how it's assembled, that image there. This is how it's assembled. And this slide is basically how it would be used. So a patient would turn the cap of the dial, and that would then allow it to tighten and loosen. So our concept 4 is simply integrating the past slide with a correct anatomical shape, and that would then result in the final product of a fully functioning adjustable socket, and it would satisfy all our specifications. And now we're going to discuss performance evaluation.
So before we could actually print the socket, we have to determine which material in the makerspace is the best. So we did material testing of the 3 different materials that we have: PLA, ABS, and resin. And once we were done, we had to analyze it. So based on the analysis that we've done, we realized that resin had a much higher elastic modulus and the yield strength compared to FDM, compared to PLA and ABS. So it also is it's not flexible, it's not too flexible, but it's also very lightweight, which is good for the design. So when doing to make sure that our design matches our specifications, we need to make sure that we had to do simulations using finite element analysis. So using a software called Console, we used the first STL file, which is the first modeling, the first CAD drawing of the socket, because it's more symmetrical, so it's easier to predict what's going to happen and for the forces. So for the functionality section, we had to make sure that it needs to be able to support 500 pounds, and this is a picture of the safety factor provided by the software. So the yellowish part here tells you that it's about 7 to 8 for the safety factor, which means that this part of the socket is to withstand a force of about 7 to 8 times the intended weight, which is 500 pounds. And we could see that the socket is more vulnerable to the base and the extremities right here. We also have to make sure that it fits. A good way to make sure is to just measure the diameter of the socket. And we also one of the specification was to make sure that the socket was comfortable. Based on the analysis made in Console, we realized that resin is not ideal for comfort. So one of the solutions was to use a silicone liner on the skin before inserting the socket for comfort. And also one of our specification was to be quick to fabricate, so quick to make the socket. And when printing the socket, which is about 75% of its actual size, we can realize that it takes about 6 hours to print 75% of the actual size of the socket. We were not able to print the whole 100% because of the machine as some constraint. So it could only go up to about from the cost analysis. So when manufacturing the socket, it takes about $14 to actually print one socket. It's pretty great because the whole purpose is to stay below 500. And the cost analysis. So we need to factor in labor, and we to factor in labor and to know how much it takes. We need to know how much a bioengineer makes, which is about $51.42 an hour. So labor would be close to $300 for 6 hours of work, approximately. So the total cost would be about $332 to make the socket. And risk analysis, that's we use the ISO standards, which is the ISO is the International Organization for Standardization. It tells us what standards to follow when making a medical device. So these are the one we follow for our medical socket. And it's also ISO 10993, which is non-cytotoxic, making sure that the material that we're using is not toxic to human cells and there's no irritation or allergies. And some question that we were asking ourselves when making the socket were, is the material safe for the skin? Is it durable? Is it reliable? Is it affordable? Because the whole purpose was to make something that's reliable, comfortable, and affordable. And that's the actual project timetable. So these are some limitations and constraints. So the main ones being the material, we were very limited in terms of materials to actually print the socket, and also the 3D printers were not the best, they're not industrial 3D printers, and also the 3D scanners were also not the best. So these are some lessons learned, some starting from designing, some 3D printing, 3D modeling, material testing of materials, etc. And also, we would like to thank Dr. Roche Guzman and Dr. Professor Mohamed Abdelmegeed for everything they've done for us this semester. Also, Dr. Salvador Rojas